All right, ladies and gents, let's take a look at the second derivative of parametric curves. If you take a look at the last video, we used the example x equals t squared, y equals root t plus 3, and from that we were able to find dy dt over dx dt simplified to 1 over 4 t to the 3 halves power as our first derivative, right? That is dy dx. So how can I then find the second derivative? D squared y over dx squared. Well, first, we're going to go through a little bit of a proof in terms of where this comes from and how we're going to find the second derivative, how we sort of get to that method. So the second derivative is the derivative with respect to x of the first derivative. Right? Like that's all the second derivative is. Well, but we also know that dy dx, when we talk in terms of parametric curves, is really dy dt over dx dt. So if we can write it this way, let's do a little fraction multiplication across our numerator here and have ddx of dy dt over dx dt. And if we treat these differentials as little individual factors here, we can rewrite this numerator as ddt of dy dx over dx dt. And this result is actually really, really useful because think about the information that we had from before. We have dy dx. We know dx dt. So we can take the derivative with respect to time of dy dx, put it over dx dt, and that's going to be equivalent to our second derivative. So how does this actually work? Well, let's take the dy dx we had from before. We're going to take, let's switch our colors here. We're going to take the derivative with respect to time of our dy dx, which was rewritten 1/4 t to the negative 3 halves power. We're going to put that over our dx dt. We have that too. If you remember back from before, our dx dt was 2t. So what's this equal to? Well, let's dig in here and go to work. Take the derivative. Negative 3/8 t to the negative 5 halves power over 2t. 2t was our dx dt from before. Now, I always like to write this in a simplified form before I actually go to work and use it. So how about negative 3 over 16, 2 times 8, and then if I bring this down to the denominator, I get t to the 7 halves power. That's the same thing as writing negative 3 over 16 times the square root of t to the 7th power. Now, in our previous example, we looked at this graph specifically and looked at the tangent line that existed at the point 16,5. This tangent line was created at the time 4. Well, what about the second derivative at the time 4? At time 4, couldn't we use the second derivative to determine if we are concave up or concave down? Let's put 4 in here. If I take my second derivative, d squared y over dx squared, evaluated at time equals 4, I get negative 3 over 16 times the square root of 4, a little room here, to the 7th power. And that's some big number, right? 16 times 2 to the 7th in the denominator. But the biggest news here is that this is less than 0. This is negative. This means that at time equals 4, we have a concave down curve. Take a look at our graph. We have a concave down curve specifically at all times through this sort of zone here, but specifically at time equals 4 at the xy point 16,5. So to review, whenever we're finding the second derivative, really the second derivative is, bring it back here, the derivative with respect to t of dy dt over dx dt again. So first you're going to need to find your first derivative and use that result to get to your second derivative. I hope that helps. Good luck.